All right, so we're going to be talking about lesson 3 on the Coulomb's law. Super new names. I don't know if you remember learning about Coulombs in grade 9. When we talk about Coulombs, it's a unit that is used to measure charge. So charge has a symbol of Q, and it's measured in the unit of Coulombs. Okay, I don't know if you remember, like you way back in grade 9, you would have learned, or even in grade 11, I think we did talk about current as I equals Q over T. I don't know if you remember that at all. Q is the coulombs, okay? So, recall again, it's called law of charges. You should be aware that opposite charges will attract each other and similar charge would repel. The reason why we would be talking about it when we're talking about Coulomb's law is you need to know which way the forces are. We are going to be dealing with forces that has to do with electric forces. I know it's Fe again. Elastic force is also Fe. It is exactly the same symbol. Okay, but we're now talking about electric force. Okay, if I have an object that is minus, and if I tell you that there is a positive charge beside it, and I'm asking you if I focus on this negative charge, and I'm asking you between this negative and positive, negative charge, which way will this electric force be going, acting on this yellow dot? The answer should be it's going to the right. The reason for that is I know that positive and negative, they actually have an attraction together, right? So when they're attracted to each other, that means they're going to have a pull, right? So that means feeling from this point, I'm going to be feeling a pull towards the right, okay? Vice versa to that, if I change the situation and I say, how about if I have a positive charge and then another positive charge, and I'm asking you, what is the forces that are acting on this, okay? I know that they are like charges and like charges repel. Okay, when they're repelling, that means there's going to be a push against each other, away from each other. So if I'm asking you what is the overall force that will be felt by this object right here, this positive charge, because there is going to be a repelling, it is going to be pushing against and or away from each other. The direction of the elastic force is going to be towards the right. Okay, right? So vice versa, like chance, like things like that, right? So when they're attracting, they're going towards each other. When they're repelling, they're going away from each other. Okay. All right, so that's why we need to know the law of charges. Finishing it up, charged object can attract subneutral objects. Okay, and then we have a law of conservation of charge. They're saying that if there's in any case any transfer of charge from one object to another, the total charge of the closed system will remain the same. And this usually applies to like a static system. And that's why when we in grade 9, we talk about charge of contact, charge of induction. But in here, we're not going to go into super details. Okay, so basically what happened is we have been through gravitational, Newton's law of gravitation when we did the equation Fg equals gm1m2 over r squared. We call that relationship the inverse square law. I don't know if you remember, but because of the r squared that is at the bottom, if I double the distance, it means that I've actually made it 4 times smaller. Okay, and they hypothesized that electric forces has the exact same effect. And then of course, scientist Coulomb, he established a relationship and he found that the electric force is inversely proportional to the distance between them, and they're directly proportional to how strong each of the charge is. So he puts the equation together, and this is called the Coulomb's law. Okay, so this itself is the Coulomb's law. Okay, studying it a little bit. So Fe is measured in newtons. Okay, and then variables, you might or might not know them, but the Q's are measured in coulombs. We talked about that. Distance is measured in meters. Okay, so if you take a look at the K is the constant again. Very similar to the capital G in the Newton's law of gravitation, but this time this is the Coulomb's law, K constant. And this is called the Coulomb's constant, K, and this is the value. Okay, 8.99 times 10 to the 9 newtons meter square per coulomb square. Does that unit make sense? Let's just quickly write it out. So Fe is K Q1 Q2 over R squared. To rearrange for K, it's FE R squared divided by Q1 Q2. I just rearranged the relationship. And since I know FE is in Newton, meter square, R square is in meters, and then Q1 and Q2 is your Coulomb square. That's where this unit came from. Okay? All right, so that means you every time when they're asking you to use the Coulomb's law, you already have the K. Right? So Coulomb's law, so just like what the equation is saying, the force is of any 2-point charges is inversely proportional to the square of their distance. So that's why it's divided by R squared. And then it's directly proportional to the product of the charges. That's why the Q1 and Q2 is at the top. And the direction of the forces is along the line connecting the two objects. We don't put in the sign when we do the math. Okay, like even if they say a proton and an electron and you have a positive or negative, we do not include them in the equation. We use it like a vector diagram. Okay, we would deal with these questions like a vector diagram, just like any forces. Okay, we deal with it as a vector diagram and we would add it or subtract it, whatever. Okay, are equal in opposite directions. Okay, so let's just talk about this again. Okay, I know the equation is FE is K Q1 Q2 over R squared. If I have something that's a plus, if I have something that's a minus, and I tell you that the Q1 is whatever value and Q2 is whatever value, when I put it into the force equation, the Q2, I would not put it as a negative 5 coulombs. I don't put the sign in the equation. Okay, but what I do is after I'm done the math, I do put a direction of where it should be going. Say if I'm focusing on this charge right here, they are opposite charge, meaning they're attracting, meaning the direction would be to the left. That means I'm going to write the direction is to the left. Okay, very good application types of question. Talking about similarity and differences between the Coulomb's law and the law of universal gravitation. Okay, both are inverse square law. Okay, they both have forces acting along the line that is joining together by the distance r measured from the center of the object. Okay, difference. Electric force, it can attract or repel, but the gravitational force only attracts. The g is very small. So the gravitational force is only significant if one mass is really, really big. Okay, while k, it's actually a very large force. When we talk about the fundamental forces, force of gravity is actually the smallest force of all, right? So here is another reason that's proved to you. Force of gravity is the smallest one. Okay, so let's do some calculations here. The magnitude of the electrostatic force between two small, essentially point-like charged objects is 5 times 10 to the negative 5 newtons. Calculate the force for each of the following situation. Okay, the first one, the distance between the two charges is double, while the size of the charge stays the same. So they tell you the original force, Fe, is 5 times 10 to the negative 5 newtons. And they said that in a new situation, what happened is they tell you now the distance is double. Okay, so R2 is 2 times of R1. This is the first one. Okay, so what would happen to the actual force itself? Okay, so they're asking you to go to this thing called the inverse square law. Go back to the force of electric equation, Q1 Q2 over R squared. So they're basically asking you, if this is the original one, what would happen if I actually double the radius, okay? But with keeping everything else the same. So what happened is if I doubled the radius, okay? So let's take a look what would happen. These are called ratio questions. Sometimes you guys hate it. Okay, so the new one, this time, the K Q1 and Q2 stays the same, but instead my radius is different by double. Okay, so when I do that, what happened is, let's do the math and see compared to the original to the final. Okay, so I have equals K Q1 Q2 over, instead of 2r to the square, I have 4r squared. Okay, now I'm going to block off the original one. So that means, do you see how these two are exactly the same? And I know that all these equals to 5 times 10 to the negative 5. So I'm going to be replacing this. So I'm going to know that I'm replacing the original force, but this time I have to divide it by the 4, the new 4, because that is what happened. This is called the inverse square law. I double, meaning I make it 4 times less. So 5 exp negative 5 divided by 4. I get 1.25 times 10 to the negative 5. So 1.3 times 10 to the negative 5 Newton is the new one. Okay, this is part A. Part B. Okay, part B, they now tell you the charge of one object is triple, while the other charge is half. Okay, so FE, I'm going to call this part, I don't know, I'm going to call it B. Okay, part B, K, Q1, I have triple one of the charge, and I have half the other charge divided by r squared, assuming that the distance didn't change. So 3 times 0.5 is 1.5 K Q1 Q2 over r squared. Block off the original one. So I know this is the original one, K Q1 Q2 over r squared. Oh, that's a square. And then I'm replacing it by 5 times 10 to the negative 5. So this equals to 1.5 times 5 times 10 to the negative 5. 1.5 times 5e negative 5. So 7.5 times 10 to the negative 5 newtons. Okay, and then if they happen simultaneously, I basically would take care of the 1.5 and the 4. So for part C, would be 1.5 multiplied by 1 over 4, because that's the factor right here, times 5 times 10 to the negative 5. So the effects are all happening together. So I double the charge, I triple one of the charge, half the other charge, and then I double the distance. So 1.5 divided by 4 times 5e negative 5. Oops. 5. I got 1.875. So 1.9 times 10 to the negative 5 newtons. So question 2 is asking for the magnitude. What is the magnitude of the force of repulsion between two small spheres 1 meters apart if each has a charge of 1.0 times 10 to the negative 12? They're asking for what is the force, and is the electric force that I'm looking for. I know that the distance between them is 1 meter, so that's r, and both of the charge, Q1 and Q2, both equals to 1.0 times 10 to the negative 12 coulombs. So the equation, the Coulomb's law, is KQ1 Q2 over r squared. Plug in what you know. So notice K, that means you need to realize I have a K. So you go and look at your constant. So 8.99, just like any constant, after you do it 10 times, you would already know this answer, this number, but that will always be given to you anyway. Meters square, actually, okay, Q1, Q2. So because they're the same, is it okay if I just write that they're to the square? This is Q1 times Q2 and they're the same thing, and then radius to the square. So just like the gravitation, the biggest issues is all the big humongous number, right? That's the annoying part, but also the important part. So definitely suggest you double check your work. I got 8.99. Okay, so worry about your SIGDICs after. I should have written it out in the SIGDIC. So 2 SIGDICs, so 9.0 times 10 to the negative 15 newtons. Question 3. Okay, charged spheres A and B are fixed in positions as shown, and they have a charge of 4 times 10 to the negative 6, which is a positive, and negative 2.5 times 10 to the negative 7 for A and B. Calculate net force on C, whose charge is 6.4 times 10 to the negative 6. So we're focusing on the charge, the force that is acting on C. So what that means is I need to work out what is the force between A and C and what is the force between B and C and what directions. Okay, so let's take a look at A and C. So I'm looking at, I will erase these marks because I don't want too much mark here. But at this point, I am looking at the forces between A and C. So ignore picture B, right? So ignore this, okay? I need to know what is the force acting on C. Okay, C is positive and A is also positive, they're repelling. So what that means is the force between A and C should be pointing towards the right because they're repelling, pushing against each other. So the force between A and C would be towards the right because they're repelling. Okay, now I'm going to take a look at between B and C. Okay, between B and C, B is negative, C is positive, and when they're positive and negative, they're attracting. When they're attracting, meaning C would feel the pull from the B, so the F between B and C would be towards the left-hand side. Okay, so we're going to be dealing with vector sum. We're going to separately work out what FAC and what FBC is, and then later on draw a vector diagram to decide where it's going to go. Okay, so the equation is KQAQC divided by the radius, meaning distance between AC to the square. Write the same equation, KQBQC divided by the distance between B and C to the square. So 8.99 times 10 to the 9. A is 4 to the negative 6. C is 6.4 times 10 to the negative 6, all divided by the distance between A and C is 30 centimeters, so it's 0.3 meters squared, right? So SI unit would be important. Okay, so is it okay if I say distance between A and C is 30? Okay, so now punch it in your calculator. Okay, so 2.55716 to the right. Okay, so this is what I got. And I'm just going to write down the direction as well. This is to the right, force AC. Okay, now I'm going to do the exact same thing for B and C. B, the charge of B is 2.5. Remember, we don't put in a negative. I almost wrote it, but don't put in the negative. Don't put the charges in. C is 6.4 to the negative 6. Distance between B and C is 10 centimeters, so 0.1 meters to the square. 2.5 times 6.4. Okay, so I got that to the left. So overall, if I have one that's going to the right and one going to the left, I'm going to subtract it. So the right number is bigger. So the F net, the overall net force, is going to be 2.557 minus 1.4384. So 1.1. So the overall answer, I'm going to keep it in two significant digits. So 1.1 newtons to the right. Okay. Identical spheres A, B, C, D with a charge magnitude of 5 times 10 to the negative 6, situated at a corner of a square whose sides are 25 centimeters long. Two diagonally opposite charges are positive, the other two are negative as shown. Calculate the net force acting on each of the spheres. Okay, I'm not going to do each of them. Let's just pick one. I'm just going to do this guy. Okay, so let's study this first. So just like what we've been doing, we basically would find out what the forces are acting on each of the spheres. Okay, like, so on part A is going to feel B. Because A is positive and B is negative, the net force is going to be going to the right between A and B. So I'm just going to draw FAB going to the right. Are you okay with that? Right? They're attracting their opposite charge. Okay? Between A and D, okay? Between A and D, they're opposite charge. They're attracting, so that means the forces is going to be pulling towards the D. So FAD is going to be downwards. Okay, and then the last one is between A and C. Between A and C, they're the same charge, so they're repelling. So that means I'm going to feel a force. I'm just going to change colors so we're color coordinated. Let's do green. Okay, between A and C, they're repelling, so it's going to be pushing this way. So FAC, it's going to be that. The distance is 25 centimeters and also 25 centimeters here. The only distance that I need to figure out is the distance between A and C. So this is a right angle triangle. So if both sides are 25, so let's find out the radius between A and C. So Pythagorean theorem. So the distance between A and C is 0.25. And then take the root. It's 0.35 meters is the distance between A and C. So I'm just going to separately calculate each of the force first and then add them all together as a vector. Okay, let's start with the first one. So FAB is going to be KQA over RAB squared, the distance between A and B. So throw in what you know. Each of the charges are the same, so I'm just going to put them as square. The only thing that I can screw up now is I'm not careful with my distance, and then, or maybe I forgot to square them. Okay? 9,5e negative 6 squared divided by 0.25 squared. So 3.596 newtons. It is to the right. I'm going to do the same thing for the red part. FAD is going downwards. Same equation, except this time the distance is between A and D, which is also the same length. So this is the same as the question just now, going downwards. So the last one is FAC. So KQA, all divided by radius of A and C square. Okay, so 8.99 times 10 to the 9. The charges are the same, so the square, all divided by 0.35 to the square. Okay, so 1.798 newtons. The angle is up 45 degrees to the left. Okay, I know this is like, why is it 45? So yes, you are supposed to prove your angle where what it should be. So this is a 90-degree angle. These two sides are the same, so they're an isosceles triangle. So I know that because of ITT and isosceles triangles, and then also for angle sum of triangle, I know that this angle theta, these two angles must be the same. So 180 minus 90 and then divided by 2. So the angle theta would have to be at 45 degrees. Okay, so now that I've gotten that done, you now can figure out what is the overall net force. So because there are three vectors here, right? There is the one that, there's the one that's going to the right. I meant the highlighter. The one that's going to downwards, and then the one that's going kind of on an angle. Because there's more than three, I feel that it's easier if I do components. So I'm just going to quickly work out what the component is. So I think the key point is the green one. So if I have something that's traveling this way, and this is 1.798 and the angle is 45, so I can quickly work out what are the component. So this bottom one along x going to the left hand side is going to be 1.798 cosine of 45, and then this is 1.798 sine of 45. So now sum up all the forces along x and y. So let's see, along the x direction, I have this force and this force, right? One is going to the left and one is going to the right. So this is left, right? So do you see how 3.56? So the F net along x is going to be 3.596 minus 1.789 cos 45. 1.798 cos of 45. So this is 2.3246. I'm just going to write that. And that one is right and left. Right is bigger, so I'm going to have right. And then along y, let's change color. Along y, I have one that's going down and one that's going up. Okay, down is bigger, so F net is down minus up. So I'm going to take 3.596 minus 1.798 sine of 45. And it should be the same value because it's the same thing. So 2.3246 Newton. That is going down. So finally, when I have these two, one is going to the right, one is going down. They're both 6, so then now I can find out what my resultant is. So finally, this is my F net. So Pythagorean theorem, and I need to figure out what is the angle. Pythagorean theorem. So 2.3246 square, adding the square times 2, take the root, so 3.3 Newton. And the direction, because this is a right angle triangle, and I can use tangent, and the two sides are the same, so it's 45. So finally, it's right 45 degrees down. Ooh, big question, okay? But basically, it is a vector question with you knowing how to calculate F between charges. One last thing, just commonly used value that you might find useful. I don't know if it's on your sheet. Micro means times 10 to the 6. So if they ever give you something like 15 micro coulombs, it really means 15 times 10 to the negative 6 coulombs. Okay, so you basically replace that with the placeholder. Nano is negative 9. You also might need charge of an electrons or the charge of a protons, okay? Because sometimes they say, oh, this object has 5 excess electrons. Then they actually gave you the Q, because you have the constant for one electron is 1.6 times 10 to the negative 19 times that by 5 or whatever the number